Okay, so in the last couple of videos, we've been talking extensively about how to approximate limits using either the graphs or the numerical representations of those functions. And what we want to do now is finally move from approximating those limits to actually evaluating them. So the first thing that we're going to do is we're going to notice that limits are preserved by arithmetic operations. That's a clunky sentence to say, but we'll go through what that means, and it's a pretty obvious thing once we see it. Then what we're going to notice is that limits are going to work really, really nicely with certain types of functions because of the way that they work with these operations. So specifically, we're going to look at polynomial functions and rational functions. And along the way, we'll remind ourselves of what that means, what a polynomial function is, what a rational function is. And then finally, we're going to use the fact that the limit itself of a function does not rely on the function value at that point. So we'll be able to reduce some weird problems to something a lot more manageable just by using that little property. So here we go. We're going to start off with some operations. Our four basic operations are addition, subtraction, multiplication, and division. So we're going to start with two functions where we're going to assume that both of the limits exist. If you wanted, we could call one of them L and one of them M, but it doesn't matter what they actually are. It just matters that they exist here. And here's the stuff that we've got. So here we can see that if you have two functions that are added together, we can almost do something like the distributive property where we split them up into the limit of each function. The way that we say this is that the limit of a sum is the sum of the limits. So you can see we're applying the limit to the sum of these functions, and that's the exact same thing as the sum of each of the limits of the functions. You'll notice the same thing works for subtraction. So we could say, all right, instead of just looking at one function that's really the difference of both, we can split it up into each function separately and apply that limit to each. So the limit of a difference is the difference of the limits. We have the same thing with products. The limit of a product of functions is the product of the limits of those functions. And we have the same thing with division. You can apply a limit to a numerator and denominator. So the limit of a quotient is the quotient of the limits. The only thing with division is we still have to focus on making sure we don't divide by zero. You've probably learned for as long as you know how to do arithmetic with division that dividing by zero is bad, and it still is. So as long as these limits exist, and in this case, the new denominator limit isn't zero, then we can do all of these operations in a way that probably feels pretty natural. We just look at each piece individually and then combine them back together. Notice that these rules all hold for one-sided limits as well, which should make sense. If the two-sided limit of a sum is the same thing as the sum of the two-sided limits, then for those two-sided limits to exist, the left and the rights had to be the same thing, right? So of course the left side limits are going to act the exact same, and the right side limits will act the exact same as well. So one-sided limit statements like this would work as well. Okay, so those are our four basic operations, and now we can start putting things together in a couple of different ways. So here we're going to take a look at constant coefficients. What happens if you take a function and you just scale it? You multiply it by 2 or a half. Then we'll take a look at some integer exponents. What happens if you raise a function to the 4th power? What happens if you raise it to the negative 4th power? And then we'll take a look at rational exponents. Those are really roots though, right? A half exponent is really a square root. So we'll take a look at something like that. So here we go. For constant coefficients, it acts exactly the way that you'd think. You can kind of factor these out of our limits. And that's the same thing as this constant multiplied by the limit of the function. This notation here just means that k is an element of the set of real numbers. This just means k is some fixed number. Here in this next one, we'll talk about integer exponents. You'll notice that if you take some function and you raise it to the nth power, that's the same thing as raising the whole limit to the nth power. And here we'll say that n is an element of the natural numbers, meaning n is like 0, 1, 2, 3, etc., etc., etc. So we're talking about positive integers or non-negative integers, really. For rational exponents, we'll have the same kind of thing with n and m. They're both these natural numbers, 1, 2, 3, 4, 5, blah, blah, blah. But now we're looking at these roots, right? Notice that when you divide by m in the exponent, that's really an mth root. That sounds weird to say. An mth root. And we'll notice the exact same property here. You can apply this exponent to the whole limit, which means you have the mth root of this limit raised to the nth power, which is kind of weird. The only tricky thing is that if m here is even, if you have an even root, we got to make sure that there's not negative stuff underneath. So we just got to make sure that our function values aren't negative for all the x values around a. That way, as we're approaching from the left or from the right, we don't have any non-real values here. There are some cases where we can think about what that would mean, but for now, we'll just wrap it up this way. All right, so what we're going to do now is take all those weird jumbly properties, and we're going to start putting things together to build two classes of functions, which are going to work out really nicely for us. We're going to think about limits of polynomial functions, and we'll think about limits of rational functions. So to start, we're actually going to look at two really small functions, and I'm convinced that I can at least convince you of these rules that we're going to have pretty easily within 30 seconds each. So let's think of a constant function y equals k. If you want an example of this, then we can just think of like y equals 2. And what we should probably do is think about what the graph of y equals 2 looks like. A constant function is just a horizontal line. And so here's our function right here. And it goes forever in both directions. And so now what we want to know is as x approaches some value, what do the y values get close to? Well, let's pretend a is over here. As we approach this point on our graph from the left and the right, what are the y values doing? Well, they're always 2 by definition, so probably they're getting close to 2. If you move a over here, that doesn't change things, right? If all the y values are always 2, then the left side y values and the right side y values are always 2, so this limit is always 2. So that means that the limit of a constant is just whatever that constant is, k. If we had changed this y value to -7, we'd have a horizontal line way down here where all the y values were -7, so every single limit on this function is -7. All right, next one, the identity function. The identity function is this nice diagonal line going through the axis, right? Or the origin, I mean, right here. And the whole point of this line is that the x values and the y values are always the same. So that means if you've got some value a here, the y value has to be a as well, right? Because every point looks like this. So as you get really close to this x value a, what are the y values going to get close to? Well, obviously they're going to get close to a, right? This limit right here seems kind of circular when we talk about it. We're going to say as x gets close to a, what does the output x get close to? Well, if x is getting close to a, then x gets close to a. That seems like a silly sentence to say, right? All that to say, though, for the identity function, it's always just going to be whatever the x value is that we're approaching. So constants stay constants, and this identity function, y equals x, just spits out the y or the x value that we're approaching. All right, so let's take all that, put it together, and build the limit of a polynomial function. Whew, this stuff looks wild. All right, let's talk about the notation. We have all these coefficients. I'm going to call them c sub k. So we're going to number our coefficients, the 0th one, the first one, the second one, the third one, up to the nth coefficient, whatever. And they're all real numbers. That's what this notation here says. These are just numbers. We'll make sure that c sub n isn't 0, because that would mean this whole term was 0, and then we'd just call this one c sub n instead, because n is the degree of this function. All right, so this is a polynomial. Coefficients times x's raised to exponents, add them all up. So what we want to do now is take a look at this limit and see if we can use those properties to make it look a little bit nicer. Notice what we have is a bunch of sums here, right? We're adding all these pieces together. And we saw earlier that the limit of a sum is the sum of the limits. So this is really the limit as x approaches a of c sub n x to the n plus the limit as x approaches a of c sub n minus 1 x to the n minus 1 plus, and we're going to do this for all of them, we'll just put the limit on each term here. C sub 2 x squared, the limit as x approaches a of c sub 1 x to the 1, which is really just x, plus the limit as x approaches a of c sub 0. And then what we'll notice is that we have a whole bunch of coefficients. These coefficients can just get brought outside the limit. And then what you'll notice is that all of these terms are just x's raised to exponents, and that means we'll have a limit inside of the exponent, and this is a constant. So this one we already have. All right, so let me write out what this is. I'll try and write a little bit smaller so I can fit everything. We're going to have c sub n times the limit as x approaches a of x raised to the n, plus all of the same kinds of things until we get down to c sub 2 times the limit as x approaches a of x squared, of x squared, we'll square the whole limit, plus this c sub 1, oh boy, here we go. The limit as x approaches a of x plus this constant, which we can just write as c sub 0. All right, and then all of these are just a, right? Because these are all identity functions. So what we end up with is just this polynomial function evaluated at a, right? This is the exact same thing as if we just plugged in a for x on all these spots. So our rule for polynomial functions is that this limit here, as x approaches a for a polynomial function, is always just equal to the function evaluated at a. This is different than what we've been talking about earlier. We said that they aren't necessarily related to each other, the limit and the function value. But with polynomial functions, they have to be the same thing. Well, that's kind of cool. All right, for rational functions then, this ends up being really easy to do because we can say this is a quotient. So let's just go ahead and put the limit in the numerator and in the denominator. And the main definition of a rational function is that the function in the numerator and the function in the denominator are both polynomials. So let's go back here and say, wait a second, polynomial limits are super easy. You just evaluate the function. So this is p of a over q of a. And we got to be careful about one thing. Probably don't divide by 0. So that's it. Rational functions are easy too, as long as you don't divide by 0. Right? Okay, so here's 3 examples. Take a look at these. Each of these are polynomial functions or rational functions. So go ahead, pause your video, and see if you can do this. I'll give you a hint. The first 2 are super easy because all you have to do is evaluate these functions at these x values that we're approaching. The third one might be a little bit weird because you might notice something happen in the denominator. All right, go ahead and try that. All right, hopefully you've actually gone through and done this. You'll notice the first 2 limits are pretty easy, right? This blue polynomial one, all we're doing is just tossing this x value of 3 in for x in each of these cases. Because again, these limits of polynomials are the exact same thing as the function value. Same thing with this rational function. I'm just putting 1 in for x and evaluating this. So my first limit is 10, my next limit is -5. Things get weird here because when we evaluate this denominator, we get 0. And remember, we said this only works if you don't divide by 0, right? So sure, we can go ahead and chuck in 2 everywhere, but we get this weird 0 over 0 thing. This is called an indeterminate form. We're going to talk more about this as we go. But for now, what we're going to say is that for an indeterminate form, this limit may actually exist, it may not. The function value itself does not exist. But remember, limits and function values are not necessarily equal. For polynomial functions they are, and for rational functions they are, as long as we don't divide by 0. So all we know here is that the limit and the function value might not be the same thing. We don't know what the limit is. A little bit weird. All right, so there's my reminder. The limit doesn't care about the function value. In general, for polynomial functions, they're the same. For rational functions, they're the same as long as you don't divide by 0. So what we're going to do is we're going to take a look at this definition of a limit, and we're going to use a nice fact that we have from algebra classes that will help us go back to this weird third limit and evaluate it. All right, so remember, we're supposing that this function is defined for all x values near some value of a, except possibly at that value a itself, like that is in our case, right? Our function is not defined at whatever the x value was that we plugged in. We're looking for the values, the y values that, or the single value, sorry, that our y values are arbitrarily close to whenever x is sufficiently close to a but not equal to a. So remember, we're just looking around that point. So what we're going to do is we're going to notice that if you have two functions that are equal everywhere, except maybe at a itself, meaning f of a and g of a are not equal, then the limits themselves are equal. Because remember, we don't care about what's happening at a itself. Our x values are never actually getting close to there. So this seems like a silly setup, right? We have these two functions that are absolutely identical everywhere, or at least for the x values close to a. But if they're not identical at a, then we can still say that the limits are the same. All right, how does this actually help us? What we want to do is we want to take a look at this function. So we're going to say our function here is x squared minus 6x plus 8 over x squared minus 4. And back in the days of our algebra courses, we'd probably just, as a knee-jerk reaction, factor the crap out of everything on here, right? Factor the numerator, factor the denominator, and see what happens. Our denominator, we've got this nice difference of squares. And our numerator, we're looking for these values that are going to add up to get negative 6 and multiply to get 8. So this is x minus 4 and x minus 2. And wait a second, would you look at that? These are the same. And so maybe you want to go ahead and cancel these out, right? And so you'd write this as x minus 4 over x plus 2. And if you were in my algebra class, you'd be wrong. Because this function as defined is not equal to x minus 4 over x plus 2. It's equal to that as long as x doesn't equal 2. Because here, the way that our function is defined, 2 is not in the domain. So we need to make sure that when we're talking about equality, that we include the same sort of domain. We match the domain up. Now, when we're talking about limits, we really don't care about this statement anymore because x is only getting really, really close to 2. So even though these functions aren't the exact same thing at the value 2, what we can do is say that the limits themselves are. So this is the same as the limit as x approaches 2 of x minus 4 over x plus 2. All right, so this makes it easy because now this is a rational function, and we can see that if you plug in 2 here, you're not going to divide by 0, right? So this is 2 minus 4 over 2 plus 2. We get negative 2 over 4, or negative half. So when we go back to this limit that we saw, this 0 over 0 indeterminate form, what that should tell us from here on out, at least for now, is that we should be looking for this second function that might be a bit different at this x value itself, but the limit will be the same. Factoring is a nice, easy way of doing that. All right, here's another way that we can do this. What you'll notice is if you go ahead and just plug stuff in, notice you're not going to get anything underneath that square root. That's going to be a problem. So go ahead and give this a shot. Square root of 4 minus 2 over 1 minus 1. We've got, oh no, 0 over 0 again. Indeterminate. Maybe it exists. Maybe it doesn't. Let's see. What we need to do is come up with a second function that is equivalent to this function everywhere except maybe at 1. And then we'll just retry the limit. So we're going to use an algebra trick here to go ahead and do this. Just like we factored earlier, what we're going to do is use something called the conjugate. So we'll take a look at the limit as x approaches 1 of this function. The square root of x plus 3 minus 2 over x minus 1. But what we're going to do is we're going to multiply this by 1, but we're going to disguise 1. We're going to call it the square root of x plus 3 plus 2 over the square root of x plus 3 plus 2. And if you multiply all this out, I'll let you do that, we get this new limit. Our denominator is going to be x minus 1 times the square root of x plus 3 plus 2. And our numerator, we have like a difference of squares pattern going on here, right? If you multiply all this out, you're going to get this square root squared. So that's x plus 3 minus 2 squared. Notice x plus 3 minus 4, that's x minus 1. So we've got x minus 1 over x minus 1 times this ugly square root thing plus Oh, there's a 3 under there, not a 2. Plus 2. The x minus 1s, they can kind of cancel out here, only because, yes, we're coming up with a different function with a different domain, but the part that we're changing is at the x value of 1, right? This function doesn't exist at 1. The one that I'm going to write here now does, but that doesn't really matter because we're just getting really, really close to 1. So the limits are going to be the same. Notice, still no square roots and negatives, no division by 0 or anything like that. We've got 1 over the square root of 4 plus 2. This is 1 over 4. So our limit is a quarter here. In this last one, we're going to do a same kind of thing, algebra tricks. All right, so let's just check out what's going on. This is going to be 1 over 3 minus 1 minus half. Oh no, you can see that's going to be 0. 3 minus 3, we can see this is going to be 0. Another indeterminate form. What do? Oh no, we're going to do some algebra here. For these, sometimes people will call them like complex fractions. I've heard students call them that, where you got fractions nested inside of fractions. It sometimes is helpful to just deal with this operation right here. Let's just go ahead and subtract these things. So this is the limit as x approaches 3 of, we need common denominators, so this is going to be 2 over 2 times x minus 1 minus x minus 1 over 2 times x minus 1. This is just me building these common denominators so that I'm allowed to subtract. Now I'll go ahead and subtract 2 minus x minus 1 in the numerator of the numerator. That's kind of weird, right? So we have 2 minus x, and then 2 minus negative 1 is really plus 1 over 2 times x minus 1, and this is all over x minus 3. Now we've got negative x plus 3 over 2 times x minus 1. And then instead of dividing by x minus 3, I'm just going to go ahead and multiply by 1 over x minus 3. It's the same thing, and now my fractions aren't so clunky. You can see that these are pretty close to the same thing, right? If we factor out a negative on this negative x plus 3, this becomes negative x minus 3, and now the x minus 3's can get like canceled out, right? So what we're left with is this limit as x approaches 3 of this different function, but it's the same as this original function everywhere except at 3. So we've got negative 1 over 2 times x minus 1. And now if you evaluate at 3, we've got negative 1 over 2 times 2, or negative a fourth. Cool. So we have some algebra tricks. We can factor, we can use conjugates, we can subtract those fractions in the numerator and go from there. But this 0 over 0 indeterminate form shouldn't be too scary for us anymore. All right, so where do we go from here? We've got some good tools now for actually evaluating limits. What we're going to notice, though, is that there's still a ton of limits that are tricky. We haven't talked about a whole bunch of different function types. We haven't talked about trig functions. We haven't talked about exponential functions. We haven't talked about logarithmic functions or anything like that. So in the next video, we're going to build up something called the squeeze theorem, which will be really helpful for evaluating some limits that are a little bit trickier. They don't match these polynomials or rationals so nicely. And then we'll also talk about some other ways of evaluating limits after that. We'll move on to different kinds of limits where maybe we're not approaching some specific finite x value. Maybe we're approaching an infinite x value. And we'll also take a look at some other ways that limits might not exist other than just the left side limit and the right side limit not matching up. So that's what we're up to after this. Hopefully that's helpful. This was a bit of a longer video. Sorry about that, but good luck as you move forward.